Hi, in this video we're going to take a look at homework number 6 assignment and try to give you a little bit of advice about how to proceed in what we're talking about in this assignment. The first data set we're going to start with is again the Australian banking data, where we have type 1 and type 2 transactions, the number of each of them. T1 and T2 are response variables time. And the first thing we're going to do is create a basic multiple regression model, M1, that relates the number of type 1 and the number of type 2 transactions to the time it takes to process them by the tellers. And we get a multiple regression model. In the first problem, we have, of course, estimated this model, and we're going to make a residual plot that has residuals on the vertical axis and the predicted values on the horizontal axis, and we make it with the scatterplot command, and you get a smoother so that you can see evidence that the residuals are more variable with larger fitted values, larger y-hats, than when the fitted values are smaller. There's less variation for small branches with small amount of activity, as opposed to bigger branches when there are some branches that have very big deviances and deviations from what's expected. And so you should notice that as the fitted values get bigger, we have a change in the dispersion of the residuals. And that's a signal that if the residuals are more dispersed and more variation depending on the fitted values, that's a suggestion that perhaps in the underlying multiple regression model, the parameter sigma is supposed to represent the same variation in the response no matter what the values of the predictors are. And that doesn't seem to be true here. There is evidence that the response variable time has a different variation depending on the size of the bank branch. And so that's a violation of the multiple linear regression model, possibly. And so one way to do that is to do like we are doing here in 5.1.2 and hypothesize that the variation function is a function of the total number of transactions, S, T1 plus T2, and that the variation function is a function of S. If that's true, then we need to construct the appropriate expression for the weights in a weighted least squares analysis. And if the variation function is really sigma times S, and we need to put it in the form of a weights expression for variance function. Remember, the weights expression would be sigma squared over W over Wi. Solving for what Wi would be, that gives us 1 over S. And so what we have done here in this code block is created the S variable, created the W weight variable, which is just 1 over S for the transact data set. Remember that the name of the data set, $, variable name, is the way to access a particular variable in that data set. So in part A it says do weighted least squares, and so we do the linear model with the response variable time, the two predictors T1 and T2, and we specify the weights being the W variable, and that produces a new set of regression output for the new model. So we want to produce that model here in part A. I've done that for you. Make sure it runs correctly. And in part B it says compare the parameter estimates. Well, the parameter estimates from the weighted least squares model and the ordinary least squares model back up in model 1, the parameter estimates are the estimate of the intercept, the estimate of the beta 1 hat for T1, the beta 2 hat for T2, and another parameter estimate is the estimate for sigma hat. And we'll talk about that one later here. I think in B what I'd like to have you do is just focus on the beta hats, the intercept, the beta 1 hat, and the beta 2 hat for the weighted least squares, and the model M1 up here. Talk about how those are similar or different, the beta hats themselves. In part C, I want you to talk about the standard errors for those beta hats from the two models, which ones are bigger and smaller. And then in part D, I want you to talk about this sigma hat estimate. Here is the sigma hat estimate from weighted least squares, 20.4. And up here, sigma hat estimate is 1,140 from the ordinary least squares model. And those are quite different. And the reason is they're measuring different things. So I want you to think about the variance functions for weighted least squares and for ordinary least squares. What are the variance functions for those? What does sigma squared represent in each of them? And hopefully you can try to explain what is going on. In problem 5.1.3, we talk about a particular branch that has 500 type 1 transactions and 1,000 type 2s, and we get a standard error of prediction, and I want you to compare that to the ordinary least squares standard error of prediction. And so the first code block gives us the ordinary least squares prediction and standard error. The second code block gives you the weighted least squares model prediction and standard error. Notice that for the weighted least squares model, you do need to specify the appropriate weight for the observation that you're interested in. Talk about what you get and what's different and similar about the two sets of output. The second problem talks about the Berkeley guidance growth data for girls again, and we estimate a ordinary least squares model explaining somatotype with some age 9 and age 2 predictor variables, and we make a summary. In the second problem, we make a slightly different model, ordinary least squares, that does not have any of the age 2 data in it, only age 9 data. And then in problem 5.2.3, we do an F-test. We compare a small model that has only age 9 predictors against a larger model that has the previous age 9 predictors, but also some age 2 data, weight at age 2 and height at age 2. So the question really is about the additional benefit of these two extra predictor variables. And we would address that through the F-test. I've given you the expression for the null hypothesis, the alternative hypothesis. Please use the output provided to give me the value of the F statistic, the p-value, and then make us a conclusion appropriately done for a test that explains what's going on in this particular test examination. Finally, we use the full model that has all of the predictors in it, and we look at a simultaneous confidence region for the height at age 2 coefficient, that is beta 6, and the weight at age 2 coefficient, which is beta 5. And here are the simultaneous confidence bounds for the beta 5 and beta 6 underlying estimates of what we think the truth might be for those generating parameters. And the crucial thing you should watch for is where is 0, 0 for these parameters. On this grid, 0, 0 would occur right here at this cross section, and you will notice that that place is not within the simultaneous confidence limits, remembering that 0 for any of these betas would imply no effect for a particular beta, for a particular predictor, and a beta associated beta value of 0 for a system that would have no effect for that predictor. So 0, 0 would be asking about the question of whether there was any effect at all for height at age 2 and weight at age 2 after the age 9 predictors are already in the model. And hopefully you'd be able to say something about the benefit of these age 2 data after you've already adjusted for age 9 based off of this simultaneous confidence region. You should get a similar story to what you find from this F-test in 5.2.3, because that really is a question about the age 2 information after you've already included age 9 information. So you should get fairly similar stories for 5.2.4 simultaneous confidence limits. Please write a summary about what this set of confidence ellipses tell you about our problem. Tell me everything that it suggests.